Should we start? We'll start. Okay, welcome everybody to the CAME Colloquium. Just a few reminders, the talk is being recorded. Please make sure your mic is muted during the talk, but feel free to leave your video on. And if you have questions, you can use the raise hand feature in Zoom or type in the chat and I'll monitor both. Great, so I'm very pleased that we have Dean Eckles here today virtually to give our colloquium. So Dean does all sorts of cool research in network analysis, social influence, social media, causal inference, and I guess all sorts of applied statistics. He, I think, might have a record for number of degrees from Stanford, which is 5, 2 bachelor's, 2 master's, and 1 PhD. After Stanford, he worked at Facebook for several years, and then he joined MIT, where he is now a professor in Sloan, as well as a member for the Institute for Data Systems and Society program. So with that, Dean, take it away.
Cool, thanks for the introduction. Yeah, anyways, I've had some great conversations with some of you already, and yeah, I thought I'd talk about some of this work in causal inference, which maybe has become a more and more interesting area to a lot of people across quantitative disciplines right now. It seems to be kind of a hot area that a lot of people are bringing new tools to. And so I thought, you know, talking about this particular work might have some interesting applied math angles to it and also expose you, if you're not already familiar, to some of the practices in the social sciences for trying to learn about cause and effect. So I'm definitely happy to take questions throughout. This work is joint work with 3 people at Stanford, Stefan Wager and 2 of his PhD students, Nikos and Han. I think Nikos is going to be on the job market next year and does all kinds of cool empirical Bayes stuff, which some of which you'll see those fingerprints here. So what I'm going to be talking about are regression discontinuity designs, but more generally talking about causal inference. And so I want to sort of set up some of the basics there, and which will also help you see some of the ways in which causal inference in a regression discontinuity design or an RD or RDD is a bit different. Okay, so when we think about causal inference, basically the starting point is usually a randomized trial. So, you know, canonical results in causal inference, and especially the ability to do statistical inference as well, like hypothesis testing and constructing confidence intervals, focuses on a randomized treatment. So we're going to have a randomized treatment, WI is binary, and then we have some outcome. What we do is for each unit, we actually posit that there are 2 potential outcomes, what that unit would do under control and what they would do under treatment. And then this process of randomization reveals one of those outcomes. So then we see YI, which is just the potential outcome corresponding to whichever treatment they were assigned to. So we can define things like this sample average treatment effect, which would be for some sample of units, what is the treatment effect among those units? Now, note that though this is a sample quantity, it's not something that we actually can observe directly, because each unit, we observe them in either treatment or control. So for all units, we either see this yi1 or this yi0. We can't actually see both of them simultaneously. So there's still an inferential problem of even learning about this for a sample. But similarly, we could be interested in some population average treatment effect just as well, if we were also randomly sampling the units that get put in the experiment from some larger population. Okay, so thanks to randomization alone, actually, we can do a lot here. First, we can do estimation. So thanks to randomization alone, we know that the simple difference in sample means is an unbiased estimator of this average treatment effect. So that's pretty nice, right? And then also we can do inference based on this randomization alone without making any assumptions about the distribution of the outcomes. So we can do exact tests of the sharp null of no effects whatsoever. That is the sharp null that y1 equals y0 for all units, no units are affected by treatment at all. So we can test that hypothesis using a permutation test, essentially. And that will have, exact type 1 error rates in finite samples. And we can also do conservative variance estimation for the average treatment effect. And this is like the Nemannian variance estimators. So I'm not going to go into a lot of detail about this, but the idea is that randomization gives us a lot of leverage here. Randomization allows us to do causal inference, and then it's not just allowing us to do sort of point estimation, but actually have hypothesis tests and confidence intervals and variance estimates, et cetera, for this estimator of an average treatment effect. Okay, so that's great. Actually, a lot of times when people really think about causal inference is when they can't necessarily experiment, right? So even in the case of observational settings where we have not intervened, we often still work by analogy to a randomized experiment. So in the absence of a randomized experiment, we might do causal inference by positing that nature, not rather than us, has conducted some conditionally randomized experiment for us. Okay, so we might say, well, conditional on a bunch of characteristics of people, it's sort of effectively random whether they end up going to private school or public school, right? Or conditional on a bunch of characteristics of patients, it's as good as random. Nature has randomized them essentially to doctors that are going to give them, this drug or this surgery, right? And so this particularly involves these pair of assumptions: conditional unconfoundedness, sometimes also called selection on observables or ignorability, and positivity. And so the first assumption says that people's potential outcomes, what they would do under treatment and control, are independent of which treatment they actually get, conditional on some covariates. So conditional on the covariates, people are being randomized to treatment and control, right? And then the second part says that they're being randomized. That is, that their probabilities of being assigned to treatment and control are away from 0 and 1. So that for any given covariate profile, people have some positive probability of being assigned to either treatment or control. So, then this works by this kind of analogy to a randomized trial. It's that there are a bunch of hidden randomized trials that nature has created for us. Okay. Even if we or nature haven't randomized our treatment of interest, so we're interested in some treatment, but that's not what was randomized, often we hope that there's some kind of shock, nudge, or encouragement that has been randomized, something that moves the treatment, that pushes people into treatment or control slightly, right? And that has been randomized. So that would correspond to the case where we say we have some instrumental variable. So people have been randomized to something that functions as an encouragement to the behavior. So for example, we might say, well, we didn't randomize people to serve in the Vietnam War or not. However, we did randomize them to the draft lottery. Now, some people served whether or not they had a low draft number or a high draft number. And some people avoided service, even if they, the draft seemingly would have picked them up, right? But this certainly was a nudge in the direction of serving in the war, right? So, so if we wanted to learn about that effect, we could use this nudge. Now, one of the ideas in both of these cases is that then we could do inference, hypothesis tests, et cetera, based entirely on this posited randomization. So we can say, well, we didn't randomize, but just as in a randomized experiment, we're going to think about there's being this finite population or finite sample of units, and then the source of randomness is how we, in the case of a controlled trial, or nature, in the case of a natural experiment, has randomized people to either the treatment itself or to this nudge into treatment. Okay. So to give you a sense of how this works, I just thought I'd briefly mention another empirical paper of mine that we did recently that illustrates kind of this approach. So in this recent paper in PNAS, we were examining geographic and social spillovers in human mobility responses to COVID-19. The idea being that basically, yes, your local policy might encourage you to stay home or to not go to certain types of locations, but there can be spillovers across different regions. And these are important to account for in that the policy in one place may affect people's behavior in another place, in part through social influence. If you go onto Facebook or you talk to your friends and they're all going out and about or not, this is going to affect your behavior. But in order to really test this, we wanted to find some kind of source of random variation in your friend's behavior. Are your friends going out and about or not? So we used the weather in the locations that your friends are in as an instrumental variable, as something that would randomly shift the behavior of your friends, whether they're going out and about or not, and see whether then that affects you. So we kind of assume that weather here is as good as random, right? But of course, weather is also correlated across places. So it's not like two counties adjacent to each other in the US are being randomized to totally different weather conditions, right? So here you can see in the bottom left, actually, weather on a few days in March that are included in our sampling. You can see there's actually a lot of correlation structure and the weather moves. So across days, there's also correlation structure. Okay. And we can see that actually we construct this pure precipitation instrument, which is how much on average the counties that some focal county are connected to on Facebook are experiencing precipitation. And then we can see that actually that affects my own mobility. So I've just bucketed, this is like a bin scatter plot, different values of the precipitation that your friends are facing. And then what is your mobility? How much are you leaving your home location? And we can see that there's this negative relationship. So this is part of a much larger and more complicated analysis in this paper about how this source of random variation that we think affects then your friend's mobility then affects you. Okay. And you can actually also do the statistical inference here entirely based on this null distribution defined by historical weather. So we just take past year's weather and consider possible permutations of different days, et cetera, but keeping a bunch of the correlation structure of the weather. And we can look at how if we use that past weather to construct how much your friends are exposed to rain or not, is that correlated with my mobility or not? And so you can use that to construct a null reference distribution. And so that's what we did here. This is the distribution of a test statistic for the association between this single weather instrument, like how much it's raining in these peer counties, and whether I'm going out and about. Now, our observed version of this association is an F statistic of around 25. In this case, for this outcome, that's the relative change in the number of Bing tiles. These are Microsoft Map tiles that are visited by Facebook devices. And we can see that our observed association is larger than most of the null associations we get by sampling historical weather and treating that as a sample from this null distribution. Okay, so my point here is that essentially this is a way of using entirely randomization that we've posited is being done by nature as a source of causal inference and statistical inference. Okay, so so that's how a lot of times in causal inference we think about what we're trying to do is find either a way for us to experiment or a way that nature has done some experiment for us that we're going to use. Okay, so maybe some of this seems familiar, etc. Now, one really now quite commonly used research design in a lot of social sciences and biomedical sciences is what's called a regression discontinuity design. And we'll try to see how this compares with this sort of common paradigm for causal inference. Okay, so here's the classic study that introduced the regression discontinuity design. In this paper, Thistlethwaite and Campbell looked at people who had either just barely gotten a high enough test score to get a national merit scholarship or not. Okay, so they looked at people who just barely had a high enough aptitude test score. This is like the SAT, right? Is how this is done these days. I guess the PSAT technically, to either get this scholarship or not. And they said this is a way of doing causal inference about the effects of receiving this scholarship, even though there's no randomized experiment here, because there's no reason to expect that people on either side of this discontinuity are sort of radically different from each other, except in the fact that they receive this scholarship. And so if we see kind of a jump right at this boundary, this is going to be evidence of effects of this treatment. Okay, so this is from a long time ago, 1960. Actually, they introduced this kind of research design, and basically nobody noticed. This wasn't really widely used except in a few other education studies. But starting in the 90s and especially in this century, has been taken up a lot, especially in economics, but also now in other fields like epidemiology. So here's another more recent example that's sort of just like that one. So this is the effects of qualifying for the National Hispanic Recognition Program for college and the effects of that qualification on college enrollment. And so similarly, this uses scores from the PSAT. This is a designation kind of sort of like this National Merit Finalist one, but it's specifically targeted for Hispanic students. And so we can see, for example, attendance at an out-of-state college, right, seems to jump right at this score, where this has all been recentered so that basically 0 corresponds to you passing this threshold for getting into this recognition program and scholarship. Okay, so you know, one of the ways to think about this is we can just kind of look at this picture and it seems like, you know, this was sort of flat and then this is kind of a big jump. So especially attendance in this example seems to jump at colleges that were heavy recruiters via this program, that sort of use this list to try to recruit those students. Here's another example. This is on grade promotion or retention in 8th grade. So basically, if you kind of fail some tests in some schools and in some states in the U.S., you'll be held back a grade. Okay, and so here is basically this cutoff where people are potentially held back, and the y-axis is your probability of being convicted of juvenile crime. And so the idea is that actually holding people back prevents them from being convicted of these crimes later. That maybe this helps keep them in the school system longer because they actually have some sort of more success, you know, reaching towards high school graduation, et cetera, and this prevents some crime. Here's another example that we'll look at in more detail. So CD4 counts or white blood cell counts are sometimes used to assign people to treatment for HIV/AIDS. In particular, for a while, there was the use of this threshold at a count of 350, you know, the CD4 count to assign people to antiretroviral therapy. In a lot of richer Western countries, now basically people are put on ART immediately, but in cases where there may be more supply constraints, something like this threshold may still be used. And so here's not looking necessarily at medical outcomes yet, but at the percent of people who are retained in this clinic, which maybe is an indicator of their ability to kind of service and help those patients for a longer period of time. And so it seems like retention at this clinic jumps 18 percentage points at this discontinuity. Okay. So the standard kind of regression discontinuity setup more formally is that units are assigned to treatment, that is that WI equals 1 for that unit. If an observed running variable, this is often this score, test score, or a biomedical assay or something like that, ZI exceeds some cutoff C, thereby revealing one potential outcome or the other, right? And so we then assume that basically we have a whole bunch of samples from this process. And so that for each sample, we're observing these pairs where we see this unit, this unit's outcome for the treatment that it's assigned to, and it's assigned to treatment if it's above this score and it's cited control if it's below the score, or without, obviously everything works the other way around if you want to think about treatment as being below the score. Okay. So one of the things to think about this is that it seems like this is really incompatible with the view of causal inference that I had before. It was sort of design based in the sense that it's based on randomization of units to treatment and control, because actually conditional on this running variable, it seems like units assignment to treatment and control is totally deterministic, right? So if we were to sort of go back to this kind of earlier assumption, it seems like we totally violate this positivity assumption, right? So that's unusual, sort of in the world of how we normally approach things in causal inference, and it suggests that you know, there's not really an analogy to a randomized experiment happening here, at least as how we've presented this so far. So, however, intuitively, people appeal a lot to randomization in the context of RDD. So people will say things like this, and this is from a paper about this antiretroviral therapy. As with most measures in nature, the continuous measures that determine treatment eligibility are subject to random variability due to measurement error, sampling variability, and chance factors that affect biomarkers such as ambient temperature. So this random variability would then imply that patients who are somehow immediately above or below some threshold are similar in expectation, just as in a randomized controlled trial. So there is appeal to randomization here. So it's common to make appeals to this. So people say often that some neighborhood around the cutoff, maybe people are randomized, right? Is this a finite neighborhood or an infinitesimal neighborhood? Are they assigned with equal probability, et cetera? And so what I'm going to try to do here is actually build up an approach to analyzing regression discontinuity designs that really brings in randomization in a credible way. Okay, so here's this ART example. They argue that whether they get immediate or deferred ART is effectively random for those patients with CD4 counts near 350. Okay, and so they say, and this gives our comparisons right around this window a causal interpretation. So kind of the outline of what I'm going to do for the rest of the talk is, so said a bit about RDDs in general. I'm going to give you a sense of some of the existing approaches. Our approach involving this noise-induced randomization, and then we've got some applications and simulation studies of this idea. Okay, so how do people think about these formally, right? I sort of gave you this sort of very intuitive explanation on this, but how do people think about this formally? So I would say the dominant approach is what could be called a continuity-based approach, which is to say that we think that the conditional expectation of the outcome given this running variable is continuous and it's smooth in some way. And so then we can say that this design identifies a treatment effect that's defined by taking limits from either side of the discontinuity. So as we get closer and closer, we're approaching something that does have this causal interpretation. And so this is sometimes called the regression discontinuity parameter. And it's this very local effect. It's telling us about the effect of this treatment on these people who are in this infinitesimal region right at the discontinuity. Now, there's some worries you might have about this. It describes this infinitesimal population. Were we interested in an infinitesimal population to start with? In practice, we're not actually analyzing data for an infinitesimal group. We have to look at data in some region around the discontinuity, maybe use a model, but still this can result in bias, and you need to potentially account for this in your inference if you want to have correct coverage for confidence intervals, et cetera. And so more recently, people are doing this kind of thing. So I would say that the dominant approach to RD, it has been to estimate local linear regressions on either side and use that to compute this treatment effect estimate, and then maybe to potentially account for the fact that those local linear regressions might be over smoothed and you need to somehow undersmooth when doing inference. Some more recent approaches, including some by my co-author Stefan Wager, have actually tried to directly exploit some bound on how wiggly this function could be and use that to do some kind of linear minimax estimation and inference. Now, one of the challenges with this continuity-based approach is that a lot of the running variables that we see in practice are actually discrete, right? Like that your test score is some integer, right? But it's pretty hard to account for in this kind of an approach. And it doesn't really seem like this meets the criteria for design-based inference, whereby we think that our estimation and inference is entirely justified by posited randomness in the treatment assignment, right? We have to instead here make assumptions about the outcome and how wiggly this function is, right? Which aren't solely based in our knowledge of how people are assigned to treatment. They depend on some assumptions about the outcome. The other approach is actually to try to really dig in on this idea that there is randomization. So this local randomization approach takes the idea that units are near the cutoff that are near the cutoff are randomized to treatment. And I mean, I guess it's sometimes a little clear to me how literally they want us to take this, right? Because if we think about the scores being random in some interval, it becomes unclear, are they still related to the outcomes in the same way? So if the test scores are locally unrelated to the potential outcomes, then it seems like the function we should expect to see is one where there's this maybe some real slope of the function, but then within this little region, it should be that the conditional expectation function is flat, right? That seems weird, and that seems usually violated by the data that we see. So that seems a little strange, right? On the other hand, if the test scores are locally related to the potential outcomes, then this suggests that perhaps there might be some causal effect of the test score itself on the outcome that isn't captured by the treatment. And this can cause us sort of other problems, okay? So usually this approach posits some non-trivial interval, that is like some non-infinitesimal interval, such that this ignorability or unconfoundedness holds within that interval, right? That potential outcomes are not related to the score in that interval is typically how this works. But this basically doesn't seem plausible, right? For example, if we think about this study of HIV treatment, these scores, these CD4 counts, are not uniformly random near the cutoff. And someone who has a slightly lower CD4 count is likely sicker than somebody with a slightly higher CD4 count. And so even in the presence of random measurement error, this doesn't imply that we have local uniform randomization. It implies there's some other more complex randomization happening. Okay, so that's what we're going to use to drive our approach, is actually take seriously the idea that there's potentially some random measurement error in this running variable. We might be able to learn about that measurement error and then make that knowledge of that measurement error the entire basis for our inference. And so in some versions of this, we will have to assume nothing at all about the outcome or this conditional expectation function for the outcome. So we're going to make these two assumptions in addition to the one I said earlier that kind of basically describes the RDD. So first, there's some kind of latent variable u that has an unknown distribution, and then the running variable is going to be a noisy measurement of it. And then that this noise is exogenous. So that conditional on this latent variable, the running variable is unrelated to the potential outcomes, to what people would do if they were under treatment of control. As in some other causal inference settings, it can be helpful to think about the idea that there's this treatment effect that varies as a function of u. So for all the people with some given value of this latent variable, we can think about what is the treatment effect for them, right? And so we could actually, for many values of u, consider what is the treatment effect for different types of people with this latent variable, right? And essentially, this object is going to play kind of a relevant role in a lot of what we're going to do. To give you a sense of how this works concretely, I'm going to show this reanalysis of this experiment in South Africa. And so here, we're going to reanalyze this with log CD4 counts as the running variable. We assume that there's Gaussian error in this in these counts, which seems to be a reasonable approximation. We then use data from another study that took place in South Africa where they have some repeated measurements of CD4 counts. And so now we can, from this kind of retest data about CD4 counts, we can use this to infer something about the measurement error distribution. And that data on these repeated measurements is going to give us some lower bound on how much measurement error there is in the log CD4 counts that are used to assign people to treatment. Okay, so that's what this is what this looks like. On the left, we have the data from this regression discontinuity design, where we see these log CD4 counts. What does their distribution look like? And actually, kind of smack dab in the middle of the distribution is this cutoff that is log 350. On the right, we have a representation of the distribution of the differences between a test and retest. And so we have Zi and Zi prime that are measured on the same person within a short period of time. And then we have this distribution here, and if you divide by square root of 2, this is giving us an estimate of what this measurement error distribution looks like. Okay, and this is somewhat well fit by this Gaussian with a standard deviation of 0.19, right? And that's what we're going to use as this kind of lower bound on the amount of measurement error that there is. So now we can use this to do inference for the effect of ART on retention. And so the original authors actually used a sort of more basic method that probably did not have correct confidence intervals. So we're going to compare our results not to exactly what appeared in the original paper, but kind of the latest and greatest. So that's one of the options is RD robust, which tries to estimate the degree of smoothness of this conditional expectation function for the outcome, and then uses some local polynomial regression, but it does bias correction to account for the fact that there's some maybe over smoothing happening, and so you need to consider under smoothing when doing the inference. So this says that there's a 17 percentage point effect on retention, and we get this 95% confidence interval. So our approach is purely identified by the exogenous measurement error that we've identified in these CD4 counts. And so we also then just use the fact that y is binary. And so this conditional expectation function has to be between 0 and 1. And so we need no other assumptions about the outcome function. And this gives us a somewhat different estimate. In this case, we have a little bit wider confidence intervals than this other approach. But we'll see this depends on how much measurement error there really is, how much randomization is really happening. Okay. Right? The idea is in this setting, there is some randomization happening. So here is a curve that represents the probability that a second draw of a CD4 count for a particular individual would be less than this threshold, such that they would have a CD4 count less than 350, and they would be given immediate ART as a function of one observed CD4 count, right? And so we can see that if you have a CD4 count that's near 350, you have a probability that some other draw would actually be on the other side, right? Basically, your probability of assignment treatment is around 50-50. And as we get farther away from this threshold, right, these probabilities are going to 0 and 1. Okay. Now, one thing to note, if you're kind of familiar with causal inference and propensity scores, you might be tempted to think this is a propensity score. It is not a propensity score because if we had the true propensity score would require that we condition not on a single measure of this CD4 count, but on the latent true CD4 count or whatever's generating these, which is the UI, this latent variable. And this is just conditionally on one measure of it. Okay. So essentially what we're doing is using this knowledge of this measurement error and this randomness in the assignment process to determine how we construct an estimator. And the way these estimators all work is that they involve constructing some kind of weighting function that is going to weight observations on either side of the cutoff, right? And this is what our weighting function looks like. Our approach is the noise-induced randomization or NIR approach. And you can see that as you'd expect, it's weighting a contrast between observations that are close to the threshold and then some farther away. And actually, in general, these will sort of have this curve where they go positive and negative in order to cancel out some of the various biases, right? And this is then compared with a previous approach from Imbens and Weger, which is sort of this approach that directly uses an assumption about continuity. Okay, so that's like the approach in practice. I can now say a little bit more about exactly how this works and dig into some of the mathematical details, et cetera, but happy to take any questions that have popped up at this point. Any questions or thoughts about this?
So I have one quick question. It seems like in a lot of your examples, although mathematically this variable z could be anything, it is truly based on kind of one score, like a count in some biological test or a test score. Mm-hmm. But have people been thinking about this? I'm thinking of like a machine learning model that takes some high dimensional vector and maps it to a score or probability, and then does that change the thinking at all in how you would do the causal inference?
No, not a lot. And I think those are great settings to do that in. I guess one of the questions for our approach would be, well, how do you learn about what the measurement error is there? What is random about this prediction? And what is random about this score for somebody? And I've been thinking about that a little bit because I'm also doing some work related to differential privacy and some of its consequences for decision making. And so there's some cases where you're explicitly injecting randomness, but you can. So yeah, I think that's a good point. There is some work on specifically regression discontinuity designs with many cutoffs, where it can be the case that you have multiple variables and there's some kind of complex rule that might not be just a function of a scalar, but is like, well, if you have at least this value on this, or at least these other two values are below this on the, so things can happen in higher dimensions. Things can get more complicated. And actually one setting that people do this a lot in is geography. So sometimes people talk about doing spatial RDDs, though sometimes other people would refer to these more as geographic quasi-experiments, because some of the arguments don't seem like they always make as much sense with geography. And a lot of times people are also unable to really take any limits towards geographic boundaries. But actually the paper by Imbens and Weger specifically looks at spatial cases, which you can think of as being, a path to considering other sorts of more complex decision rules. And so they try to come up with a weighting function based on assumptions about continuity that that will estimate treatment effects along some border.
Thanks.
Yeah. Cool. So so here are just sort of our assumptions, again, stated a little bit more explicitly, right? Is that treatment is based on a noisy measure of a latent variable. And so this produces some noise-induced randomization to treatment. And so we're going to assume that the running variable is a noisy measurement of this latent variable. And we're going to write this function alpha, which is we're going to have one for treatment and one for control. That's the conditional expectation of the potential outcomes given some particular conditional on the latent variable. And so then that quantity I introduced before, this quantity tau u, is just the difference between these two functions. So these are the true conditional expectation functions for the two potential outcomes to ask what's the treatment effect for somebody, what's the average treatment effect for somebody who has a particular value of the latent variable. We just are going to be working with that difference there. Okay. So we think we're kind of the first ones to do anything like this. So definitely people have referred to this idea that there's somehow noise or imperfect control. And actually Lee, in a different paper than the one I'm quoting here, shows that obviously this induces continuity. If you have continuous noise, then this creates continuity. And Mika Rukkanen in another paper considers some non-parametric identification of effects away from the cutoff using some kind of factor model of different test scores. He's looking at elite public schools. But all the estimation and inference relies on a parametric factor model, whereas all of our estimation and inference is non-parametric and is driven entirely by this assumption about the design that there's this randomness due to measurement error or some other kind of noise in the running variable. Okay, so how are we going to do this? We're going to consider some treatment effect estimator that's going to have this kind of a form. So we're going to be dividing by n, and we're going to have two terms. One is where we're weighting treated units, and one is where we're subtracting off some weighted combination of control units. Okay, and so if we have weighting functions that are going to satisfy particular criteria, right, that they're going to have expectation 1, right, then we can think of this as being some kind of weighted difference in means. Now, is this going to have an interpretation as an estimate of an average treatment effect, or is it a good estimate of an average treatment effect? Well, that's going to require some of our assumptions. So under the assumptions that we've specified so far, this estimator is going to have this expectation that has these two terms. The first term is some weighted treatment effect. And so it has this tau term in here. And so it's going to be this H plus is just providing some weighting distribution over values of the latent variable. And we're just integrating out over those weights. And so it's some weighted combination of treatment effects for different values of the latent variable. Then there's going to be some remaining confounding bias, from the fact that we're comparing units that are on other sides of this threshold. Okay, and so this confounding bias is going to be, here we write it in terms of the conditional expectation of the outcome, the control outcomes, given some value of the latent variable u, and how much different weight are we putting on people with that value of the latent variable in the treatment mean estimate and in the control mean estimate, right? So if for some value of the latent variable, we're putting equal weight on people with that value of the latent variable in treatment and equal weight and the same in control, then this cancels out entirely, right? But this is going to be hard to do because we have people who are on opposite sides of this cutoff, right? And so, so we're going to try to choose a weighting function that is going to produce a good estimate here, and it's not going to have so much bias, right? It's going to try to remove this confounding bias. Okay, so it's up to us to choose this weighting function. And so we're going to try to choose this H plus that's involved in this, this quantity over here that's our weighted treatment effect, so that we're targeting some relevant weighted average, right? That's going to correspond to some interpretable treatment effect that we care about. So this is going to correspond to us saying these are the people for whom we're estimating treatment effects. And then we're going to try to jointly choose H minus and H plus to make this confounding bias small. And then we're going to have some assumptions that just come from our knowledge of the outcomes and like just what bounds we have on the outcomes. So if our outcome is binary, right, then we know that it's bounded between 0 and 1, and the conditional expectation, I mean, that is the conditional expectation function, this alpha, is bounded between 0 and 1. So one thing we could target is what people often do in regression discontinuity designs, which is target this limit, taking limits from either side and just trying to estimate the average treatment effect for people who exactly have a value at this cutoff, okay? And so we'd just be saying we want to compute this treatment effect averaged for people who have ZI equals C. Okay. Now, given that ZI is just U plus some noise, then we can say, well, this is actually just equal to this integral where we're integrating out over this distribution, you know, fixing that that Z equals C. So this integrates out over some distribution of the latent variable. But it may be useful to target some other kind of weighted treatment effect estimate, right? So this is not what usually people don't start caring about, this infinitesimal treatment effect, right? So we might consider something like a policy that changes the cutoff by some amount, right? And so what's the effect for people between C and C star and C prime? Or we could even consider other policy relevant parameters that I don't think have been considered at all in the literature before, like changing the amount of measurement error. Maybe we should introduce a better measurement here, or we should take two measures and average them in some way. So that would actually also change the results of, you know, it would affect a lot of people who now are being assigned to treatment in a different way. So we could compare those two policies. What's the outcome under the status quo policy, and what's the outcome under the policy with lower measurement error? Okay. So to sort of actually implement this, to go from identification to inference, we have to do a bit more work. So we're going to end up using some kind of a ratio form estimator, not exactly what I showed you earlier, in that we're going to be dividing by the sum of these weights, because that's going to usually stabilize things. This is something that pops up in all kinds of weighting estimators. You want to often divide by the sum of the weights. We show that this estimator satisfies a CLT under some general conditions, but we're going to need to think about how biased this estimate could be. There's going to be some confounding remaining. And so we want to choose an estimator, that is, choose a set of weights that tries to avoid having a lot of bias. And so we bound the worst case bias via fractional linear programming. And we're also trying to sort of basically get relatively narrow confidence intervals. So we're choosing these weighting functions by optimizing a bound for the width of the confidence intervals. And so this ends up connecting with some things in terms of inverse problems, et cetera. So given that we have some estimator with some particular weights, we can sort of think of those weights as fixed, and then say we want to construct some confidence band given those weights. We're going to basically consider some worst case bias. What could the outcome function look like, and then what would that do to our bias? And then all of our inference is going to allow for that bias. So we're going to get confidence intervals that do not depend on our estimator being unbiased. They'll still have the correct coverage, even though our estimator is biased. Okay, this is, some of you might be familiar with this, but this has been kind of a recent development in statistics and econometrics of doing bias-aware confidence intervals or bias-aware inference, and that appears as well in some of this work by Armstrong and Colzar. Okay, so yeah, so let me skip that. So that's kind of the basic setup. So we have some results about the asymptotic coverage of these intervals. Maybe that's not the most interesting part. Okay, so one of the things we wanted to do was to evaluate this to figure out whether we can infer treatment effect estimates, infer treatment effects away from the cutoff, right? This is one of the things that this should allow us to do, is actually say, well, there's a lot of measurement error. I can actually say something not about just people who are right at the cutoff, but people who are potentially farther away from the cutoff. So we do this using what we call a constructed regression discontinuity design. Because actual RDs are sort of limited as benchmarks because we don't really know whether we're right or not. And we might not have randomized experiments in relevant settings, and they may not reveal effects that also allow us to benchmark. And a lot of the existing educational RDDs involve data that's not readily available. And so it's hard to make that advance the methods literature. So we construct an RDD from longitudinal testing data. You'll see what I mean. So we take this data from this early childhood longitudinal study for this particular kindergarten class. We use 3 years of math test scores from this data for these 13,000 children. And so the running variable is going to be their year 1 math score. And then we actually know how much noise there are in those scores because the people who have done this study and designed these tests built an extensive item response model that basically gives you a standard error for every single score. Then we're going to define our potential outcomes, yi0 and yi1, to be the year 2 and year 3 scores. So the treatment basically corresponds to an additional year of schooling. You can think of this as the treatment is whether we are measuring your outcome at year 2 or whether we measure your outcome at year 3. But what's nice about this is for every single student in this study, we actually know both their yi1 and their yi0, which even in a randomized experiment, you don't get to see. So that's kind of nice. Okay. And then we're going to observe, these ground truth treatment effects that can vary the cutoff however we like. So this is kind of what this data looks like, is that for each observation, for each unit, we have their yi0, and we also have their yi1, and we can set this cutoff to sort of reveal to whatever method we're evaluating, which set of outcomes we're revealing. If you're below the cutoff, we see, your y0. If you're above the cutoff, we see your y1. We actually work with a thresholded version of the outcome, a binary version of the outcome, because this helps create some of the nonlinearity that would be challenging here. And so we have these kind of known treatment effects where we just threshold the outcome, I think at 0.5. And then we set our noise estimate to be the lowest estimate that appears anywhere in this data set. So again, this is a lower bound on the amount of measurement error that's present. So then we can actually see how we can estimate things away from the cutoff and compare this with the ground truth that we estimate from these potential outcomes. And so on the left, we have basically this regression discontinuity parameter, which is what is the treatment effect at exactly that value of the running variable. And you can see our estimates and our confidence intervals. Our confidence intervals get wider as we go away from the real cutoff, because as we get farther from the real cutoff, people near there, most of them are not effectively subject to much randomization, right? So these bands are getting wider away from the cutoff, but we're still able to do meaningful inference pretty far from the cutoff potentially, right? And we see that our confidence intervals in all cases are actually covering the ground truth. On the right, we actually do this, this policy change. What if we change the cutoff to some other value? So we increase or decrease the cutoff. And similarly, we see that, you know, the confidence intervals are getting wider over this space, right? Not quite as rapidly in the same way because we're averaging over everybody who's in that range. And some of them may be quite randomized, even if the ones at the far away end are not so randomized. And again, we're covering the ground truth. So I also think this is just kind of a cool approach that we took to kind of building an RDD that uses real data, but that we know the ground truth in. But one of the things we also wanted to look at was a discrete running variable. So we also did a simulation study with a binomial running variable. And so we set up a case where we're going to vary the number of coin flips, essentially. So everybody has some latent variable that is the probability on their coin. We're going to flip the coin that number of times for them. That's their running variable. And then they're going to be assigned a treatment and control based on that threshold. We consider two different choices for the outcome. One is actually this kind of worst case, sort of almost adversarial choice, where right at the threshold, because we're going to make the cutoff be 0.6, the proportion is 0.6, we change it as a step function. So the conditional outcome, conditional expectation of the outcome just is a step function, right at the discontinuity. So it's kind of the worst case. The other one is just we have this sine wave. And we're going to compare our method to some other methods in the literature. This stuff using opt-RDD, which is basically this approach that's advanced in Imbens and Weger, and also very similar approach in Armstrong and Colzar. Another approach that's pretty widely used is RD robust, which uses polynomial regression, but then tries to adjust the confidence intervals to account for bias. And then our approach using either optimal bounds or uninformative bounds that don't assume anything about the outcome. And so here's what the results of this look like. You can look at the coverage of all these different methods, and basically all of them in this setting are pretty much covering at the correct rate, except RD robust actually doesn't really cover at the correct rate, especially in this step function case. And this one that we've engineered to be that actually the true function changes right at the cutoff, which is kind of really terrible for it. It doesn't cover well, but everything else covers well. How big are these confidence intervals? So how precise is our inference? And you can see that this is going to depend on how much measurement error there is. So if we're talking about more coin flips, there's less measurement error, and so our intervals are going to get wider, right? If there's a small number of coin flips, then our intervals are going to be narrower. And so you can see that our intervals are, in some cases, narrower than other approaches, like than opt-RDD or RD robust, when there's a small number of coin flips. But as there's more coin flips, and so there's less measurement error, our intervals may be sort of closer to theirs, or could be actually the same or larger, depending on the exact setup. Okay, so we think this performs pretty well in this approach. And I'd say, actually, when our confidence intervals get really wide, that reflects the fact that maybe there isn't really much randomization going on. And so your argument for how you're doing causal inference is not based on randomization, which could be okay, but it really clarifies what's the foundation here. Okay. One quick note that you might have thought, hey, didn't you say that noise could also mean that the conditional outcome function is continuous? And so, yeah, that's true. The presence of continuous noise results in continuity. So we can actually use this to imply bounds for other approaches like opt-RDD. And so we have a proof of what the curvature bounds are given the presence of Gaussian measurement error. And so you can use this to do this sort of other Imbens and Weger, Armstrong and Colzar kind of approach. We tried this with the ART study, and it gives us a bit of a different interval. And you notice that it's actually a much wider interval. This is because not all of the information that's provided by knowing about measurement error sort of makes it through to this continuity assumption. So continuity is sort of not all that's going on here. There's more leverage provided by taking this approach that there is this latent variable that you have this noisy measure of. And of course, also, this approach about implying continuity would only apply if you have continuous measurement error and thus continuous running variables, and not in this kind of binomial case that I just showed you. So just to summarize, I think regression discontinuity designs have become incredibly widely used in the social sciences, really widely used in economics of education. You see people looking at this, to assess different penalties for drunk driving. You see this applied to retention of students in classrooms. It's getting wider use in epidemiology and clinical, as an alternative to a lot of clinical trials. People like to think of these as locally randomized experiments, but the methods for them have not taken that approach. And so we've sort of basically put RDD into this really randomization design-based approach. And we think sometimes it's going to give you giant confidence intervals because you don't have any randomization happening. Sometimes it may actually give you more narrow confidence intervals and with weaker assumptions in some sense, or at least a very different set of assumptions. Now, of course, there's a bunch of RDD setups that don't really seem to involve this, like geographic boundaries. What's random there? Am I not sure which side of the boundary I'm on? Is the boundary random? There are some approaches that have thought about random boundaries. Close elections, maybe there's some randomness there, but what is the source of randomness? Well, I guess if it's rainy in the Democratic stronghold and sunny in the Republican stronghold, well, there are studies that look at that. So that could be one source of randomness, but it's probably small compared with what we're talking about. Class size, that doesn't seem like that's measurement error. We know how many kids are in the class, et cetera. So, and other things are gameable, like GPA, et cetera. What's funny is back when Thistlewade and Campbell introduced this, they said, admittedly, the class of situations to which it is applicable is limited. It turned out that then it took like 35 years, 40 years, but people discovered that in fact, this was applicable to many, many settings. And so we would say again about our approach, maybe, that our approach is applicable to some limited settings, but we think they're important settings. And people should clarify, hey, am I in a setting where really there is randomization happening and I can directly drive my whole analysis for that randomization or not? So as a recommendation for anyone doing empirical research, we'd say, think about whether there's some substantial measurement error in the decision process and actually try to collect data about that measurement error, compute, test, retest reliability, use a psychometric model, or use some known knowledge about independence of, say, binomial trials, and actually retain and present information about the scores and the cutoffs on the original scale. A lot of empirical studies sort of throw that out. And you saw earlier in the talk, everybody like reshifts things to 0. And there might be many different scores or cutoffs in different states, for example, and they shift it all into the same scale. That throws information away. So our approach, like the earlier Imbens and Wager stuff, suggests the value of not trying to project everything to like a univariate running variable that's like a distance from a border. Rather, keep the variables on the original scale and think about the randomness in them. Okay, so that's all I've got. The paper's on archive. The URL doesn't start with a V. I don't know where the V came from, but be interested in any comments or further discussion of this. And part of my point in starting out as I did is to just say, it's useful to think about how any given widely used practice in the social and behavioral sciences fits into kind of how we like to think about randomization as a basis for causal inference. And I'd be interested to, kind of explore that more. Thanks a lot.
Thanks, Dean. All right, so we have a couple minutes for questions. And I'll start off with a question on fairness, which is, it seems like in a lot of these cases, there is pretty clear evidence of a positive causal effect from, say, receiving a drug or receiving a scholarship.
Yeah.
But these people near the boundaries seem to have a strong case under your math that they are just as, it's just as warranted for them to receive this treatment. So
right.
How should people be thinking about dealing with that?
Yeah, I think that's a great question. I've been thinking about fairness a bit in a related setting as well. I guess one thought is if there isn't so much measurement error, maybe it doesn't seem so bad because actually randomization is a pretty fair way of allocating a scarce resource. So I think one of the things to think about here is that, if the thing is beneficial really for everyone, okay, then why aren't we giving it to everyone? Well, maybe there's some substantial cost associated with it, or maybe there's even negative effects for those people that are just not on the particular outcomes that I showed you, right? So antiretroviral therapy could be unappealing, like we shouldn't give even if there was no cost limitation, it's not like we should just give ART to everyone in the world, right? So there can be reasons to target, but so if it's an allocation of a scarce resource, you think, okay, maybe we're not allocating it perfectly. But on the other hand, if we're going to experiment on anyone, it's probably we should experiment on the people who we're in equipoise about. So if, say, this threshold was designed from some prior study that said, well, it's worthwhile given the side effects or whatever to give this drug to people with, score below this value, right? Then the people that we've sort of ended up experimenting on through this noise are people that we kind of weren't sure about, right? They're right at the boundary, right? That'd be the assumption, at least if, and here I'm going to make a different continuity assumption, the treatment effect function is relatively continuous, because that would say that somehow, it's continuous and monotone. Then the treatment effects are getting smaller for these people near the cutoff. And essentially the reason that they're being randomized is because we really should be sort of in equipoise about whether this treatment is worth it for them. But there may be settings where that's not really true at all, right? And the treatment effect function is not smooth and monotone, and people are being randomized who maybe are far from the cutoff or who are clearly helped or hurt. Yeah, I don't know. Maybe, do you have any other thoughts about that? I feel like, yeah.
Not any good thoughts. Well, it reminded me of kind of finding natural cutoffs in variables to begin with, which when I think about, say, grading in a classroom, one common strategy is I'm going to sort people by some score, and then I'm going to look for discontinuities in that score in order to assign the treatment, which would be the grade, which could have some effect on them.
Right.
So that seems like one.
Actually, you might think, oh, like if I sort of put the cutoff somewhere where there aren't many people, right? Yeah. You might have this intuition that now you made that cutoff somehow less random. Like people are, there's not people who are just on either side of it, or not many of them.
Yeah.
Yeah. But that would not be good for us learning from your. There's nobody cutoff.
Yeah, I worry that like in these cases with test scores for scholarships or things like that, actually the people at the boundary, there's probably like there probably is a lot of things that are going into consideration for those people at the boundary. So like people will consider more variables, people will think about them much more carefully than they would for people that are clearly successes or clearly below the threshold.
Yeah.
So I don't know.
Yeah, and I think that's one variation on this design that I did not discuss at all. What's sometimes called a fuzzy RDD, which I would say is the wrong name for that thing. Sounds like what we're doing, but it's not. Well, I would say what we're doing is exploiting some good fuzz. And a fuzzy RDD is just an RDD with non-compliance. So there's, this being on one side or the other, the score sort of maybe, is more likely to get you treated or not in a discontinuous way, but it doesn't necessarily result in treatment. And so I'd say a lot of times there's actually some more complex decision process happening. And in fact, what I showed you guys for the ART example, we only did inference for essentially an intent to treat, an intent to receive ART. But actually, some people receive ART who have a CD4 count above 350, and some people don't, who have one below because they like churn out of this clinic too fast or whatever. So, or they die. And so, there is actually sort of non-compliance there, but that could be one way of thinking about that. If there's a more complex decision process that involves a lot of discretion and endogeneity. Yeah.
Great. I should say it is 4:36 already, so people can feel free to drop off if they need to, but we have our post-talk socializing or continuing to ask Dean questions. So if you want to stick around the Zoom, please feel free.
Yeah. Happy to take more questions. Yeah.
I have a narrow econometric question as an econometrician in terms of relation to the other literature. You did mention the estimation is non-parametric, but if I followed correctly, and you should correct me if I'm wrong, then the information on measurement error that you inject is a pretty specific and parametric model, which I'm not saying is necessarily a problem, because of course there are contexts where we understand the measurement error and then that works. But then of course there are other, I'm trying to understand the trade-off relative to other projects in the literature, right? And the third last slide or something that you had, I mean, that might be the issue, that in those cases, I can't think of a good model of measurement error.
Right. Yeah, so obviously in one of our examples we use Gaussian measurement error, in another one we use Gaussian measurement error, and another one we have this binomial model. You can actually use some kind of other way of estimating the measurement error. So we don't really necessarily talk too much about how you would have come up with your model of measurement error. And in fact, all you really need is a lower bound on the measurement error. So if in fact the measurement error is some combination of a Gaussian plus some other thing, right? So there's some additive measurement error. You can just use the Gaussian and everything will be valid.
Okay.
Right? So you just need a lower bound. So that's one of the things I maybe could emphasize more. But you could also
that
use
had not been
the
obvious
model to estimate the measurement error distribution non-parametrically. But you really only need some lower bound on the measurement error in order for everything to go through. Now, if you use too low of a lower bound, you're going to end up with overly conservative and noisy inference and noisy estimation. But yeah, maybe does that help? And I do think that in some of these cases, it's like, yeah, we don't have that much. It's hard for us to figure out what the measurement error would be in vote totals or something like that in the same way. Yeah.
But does it make sense to talk about a lower bound on the measurement error? Like, does that always make sense?
Well, so if things are additively separable, then if there's two components of error, and we have one, and we have a model for that, and then there's another, I think that's going to be totally fine. Now, if there's more complicated things to be happening, and that could sort of not be fine. So, actually, I definitely, we want to be sort of modest about the idea that this does not apply to everything. And in fact, if you can't think of a way to apply it to your setting, this might suggest that sort of this design is on some different foundations. Are they weaker foundations? I don't know. They're different foundations than on randomization. Yeah. Like in some cases, I mean, there's a bunch of RDE settings where people are really concerned with manipulation around the boundary, right? So if you have an educational RDD with GPA, well, what happens after Austin chooses this cutoff is then students come to his office and complain and do extra credit or whatever, right? Because especially the ones who are really concerned about not having their GPA fall below some threshold that's important for something else, right? And so there's manipulation there around the cutoff. And it seems like that's a setting where it's going to be very difficult to apply this approach because there is not some exogenous measurement error we can say something about. Now, there is some error there. There's imperfect control. There's some exogenous error, but it's not this kind of additive error or otherwise nicely specifiable error, right? Now, the error doesn't have to be additive. You can see that in the binomial example. It's not actually additive error. It's heteroscedastic and depends on the true value. Yeah, no, I think that's a good question. Yeah.
Thanks a lot.